Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to have Greg Bronowski from Lawrence Livermore National Labs. He's a postdoc there, and he's going to come and talk to us about static analysis for message passing. Obviously a topic of interest to many people inside Microsoft, some of whom are here and some of whom are presumably watching this on the web. So, Greg.
Oh, cool, thank you. Yeah, so at Lawrence Livermore I do a bunch of things. So this is my compiler hat, but I also do things like optimizing checkpointing, looking for how vulnerable applications are to soft errors, with the parallel applications being obviously the most important ones. And this is more focused on optimization and, well, I guess you'll see all the different applications that we have for this kind of analysis. Now, the introduction obviously is that we all love parallelism, ranging from tiny machines, like individual multi-core nodes, to computers which are built up of thousands or tens of thousands of such nodes. And, in order to write applications for these kinds of machines, people have come up with tons of different ways of expressing parallelism. This is just a very short list of those possible ways. So that's good, but the bad part is the compiler side, which really has not kept up. Now, I'm not saying the compilers cannot deal with explicitly parallel applications. They can and do. A lot of them are written at language level. OpenMP, UPC, Java threads are all language level specifications of parallelism. The problem is that compilers generally translate from the original explicitly parallel program to the underlying binary representation. They don't really understand what the program is doing as a parallel application. What they typically do is they understand it as a sequential application and then do a bunch of sequential reorderings and so on, but that's about it. So before I motivate what kind of stuff I want to do, let me show you what stuff is currently done. What kind of optimizations are actually possible. So in OpenMP, you have things like, you have a bunch of read and write operations. You also have flush operations. And the rule is that you cannot reorder a flush for some particular variable with an operation on that variable. So you can take this program and reorder it to that program. Now, the set of possible reorderings is inspired by the parallel semantics of this application. But the compiler doesn't know that. It just knows that there's a bunch of sequential reorder rules that it has to follow, and it does that. It doesn't actually understand the program as a parallel program. This is another example from MPI, which is message passing. And same basic thing. You have an application which it computes some data, sends it out, receives it on the other side, computes on it. And again, based on the parallel semantics and sequential semantics, you have a couple of reorderings you can do. In fact, this reordering of these instructions is actually more efficient. It's more pipelined. Great, but again, the compiler needed to know nothing and knew nothing about the parallel structure of the application. It just knew that these sequential reorderings were legal. Great. Now, this is not the best we can do. We can actually do a bit better. People have done work on things like barrier alignment. So you have two different functions, and these techniques can match these barrier calls across different functions, which is great, because in this case, even though these two functions operate on exactly the same variables, we can show that there cannot possibly be any data races. And this is as good as we can do. And as you note, we actually do have some understanding of the application's parallel structure. But here's something we cannot do. Suppose we have this piece of code, which is an exchange with root pattern. It looks kind of like this. Root sends a message to everybody else, and everybody else sends a message back. That's fine, but the way it's written here, it's obviously unscalable. It's going to work for 10 processes, not 1,000, definitely not 10,000 or a million or whatever. It's not going to go in the long run. So what we'd like to do is notice that this is in fact what's happening and replace it with its scalable version, which is based on a tree. That would be nice. Another thing that would be nice is if we knew that assignment x equal to 15 is there and do something as trivial as constant propagation. In that case, we could just notice that all the communication is actually constant and remove the entire thing. Again, that would be nice. But we can't do that unless we have real compiler analyses that actually understand the application as a parallel program. And if we had that, we could do a lot of different things. Here's a short list of things we can possibly do. One example of constant propagation, the simplest analysis, would be if you knew that at the start of the application you read the name of some file and broadcast that name to everybody else, and then every process read that file, the buffer where you had the data is going to be identical in all processes. One, if you were to checkpoint the application, you save only one copy of the buffer, not n copies. And two, we have this problem with multi-core processors having too little memory per core. I mean, the more cores we have, less memory per core we have. If you had these redundant buffers, you're wasting memory, and you're wasting memory bandwidth fetching them. It would be much nicer if you had only one copy of this thing for the entire node, not n copies, one for every process in the node. And that's just, that's just constant propagation. And you can do a lot of different analyses to further improve the performance, improve how you visualize the application, and so on, if you knew the structure of the application. And for some quantitative results, if you were to replace, you remember that exchange with root pattern? I mean, if you were to do a broadcast, an even simpler version of it, I mean, if you were to do a broadcast in that fan-out fashion where root sends to everybody else, you get fairly poor performance. This is a broadcast on 2 bytes, and there's a number of, I think this machine has 4 processor nodes, 4 core nodes. You have bad performance. But if you use MPI broadcast, which is a tailored operation, or a bunch of tree-style broadcasts, they all outperform this pattern. And this pattern is obviously the easiest one to write manually. If you go to 512 kilobyte broadcast, same pattern. I mean, these are a blocking and non-blocking variant, but they both have much worse performance than all the other options. And if you were interested in the actual details, I can talk to you offline. But the point being that if we knew that this was in fact a broadcast, we can do much better than what the user had done. And there are example codes where people just did the obvious thing and didn't really think about scalability. But they're paying for it, and if we knew what the application was doing, we could probably do something about it. Now, to constrain the specific problem that I'm working on, I'm specifically focused on unstructured communication. So the structured problem where you have, you create a pipe, you fork your processes, the processes can only communicate via that pipe. That constrained model has already been solved, and it's a model like in Erlang and so on. I'm looking at the unconstrained model where any processor thread can communicate with literally any other processor thread. And this is the common situation in message passing and shared memory where you have lock semaphores, barriers, and so on. In this talk and in my current work, I'm specifically focusing on message passing, although the basic techniques will apply to a wider scope, but right now it's just message passing. So before I get into the details, let's talk about what we would like to have. What tool, what are the capabilities of a tool that we would like to create? Now, what I would like to see is take the traditional data flow analyses, go from the 60s all the way to today, those analyses, but move them over into the realm of explicitly parallel applications and make them sensitive to the application's parallel structure. So here's a program, same exchange with root pattern, but with that, we're going to do constant propagation on it. So what I would like to see is, so we're going to have x is equal to 15, and at that node, and we want the data flow state to say x is equal to 15. We want to propagate the data flow state across the branch, and that send point, we want to know x is equal to 15, and here's the magic bit. I want to be able to match this send to this receive and propagate that the value of that message was in fact 15. Then I want to have the receive side, and then match this send to that receive and know that I definitely communicated 16. And now we know the other side, the receive side, that x is definitely 15, y is definitely 16, to determine that this is in fact loop invariant, and know that in the end of the program, rank 0 has x equal to 15, y equals 16. Everybody else has x equal to 15. Mind you, when I say the word rank, I mean it's an MPI term that means essentially unique process ID. That's what I would like to have. And the question is, how do we get there? Now this problem is actually fairly hard. I mean, the basic complication here is that you have no idea how many processes the application may run, so you have to compile it for an unbounded number of processes. So that means that you're evaluating one of, a ton of different paths to the CFG, but these are not all non-deterministic variants. These are paths that could be executing simultaneously and interacting, and an unbounded number of them. Furthermore, the send and receive expressions we're going to be dealing with will use arithmetic expressions. So you have to match things like my ID plus 1 mod number of processes. That matches my ID minus 1 mod number of processes. And, the problem itself is obviously undecidable in the worst case, but in general, it's going to be a hard one to capture. So these are the complications people have faced, and people have tried to deal with it so far. I mean, one option has been to have a sequential application, take the CFG, match every send to every receive, and then start pruning them, based on sequential information. So if a send and a receive are on the wrong side of a barrier, they cannot possibly match. Remove that edge. If they have, MPI allows you to have numeric tags. If those numeric tags cannot possibly match, well, remove that edge between send and receive. That basically works, and it's simple, but obviously it's not going to be all that accurate. The other option people have looked at is overcoming this unbounded number of processes problem by literally picking, I'm going to do this for 10 or 1,000, 10,000 processes and replicate the CFG that many times, one for each process. Then, when rank 0 says send to process 1, 2, 3, 4, it literally would do that. Of course, this means that that loop would have to be unrolled and you have to execute it one for every recipient, but it basically works. The problem is obviously that it's not flexible because you have to pick the number of processes ahead of time, and it's just going to be unscalable. You're not going to run this analysis for 1,000 processors. You have to run it on 1,000 processors at the very least. So it gets dirty at that point and not very useful. But we can do better than that, and that's the focus of this talk. Specifically, take the intuition of having a CFG for every single process. And the first thing we need to note in order to optimize that is, well, we don't need a CFG for every single process. We only have a couple of different behaviors, a finite number of different communication behaviors. In this exchange with root pattern, we only have two, root, non-root. And every process within each set does exactly the same communication pattern. Well, that means we only need two control flow graphs, one for root, one for non-root. So that's the first major optimizations. Don't deal with processes, deal with process sets. And in any realistic program, there will only be a finite number of process sets. And you'll be able to abstract away all the communication differences between them because they'll do exactly the same communication pattern. The other intuition to have is that we don't really want to be operating on a bunch of different CFGs. We want one CFG that corresponds to the parallel application. So every node better be the state of the parallel application. So what I mean is that would be a node. So this is a node where rank 0 is at this CFG node and rank non-zero, like every other process, is at this CFG node. And we transition from this node into this node or this node. That is going to be our parallel control flow graph. And for example, this node would be a state where rank 0 is at a receive and rank non-zero is at a send. For example, in this case, we might transition from this node by matching the send and receive and moving on. That's the kind of graph we're going to be working on. It's going to be called the parallel control flow graph, not surprisingly. The states, and intuitively, it's the Cartesian product of the CFGs of individual process sets. So intuitively, the nodes of this graph are going to be the states of the parallel application. So they're going to be tuples, finite tuples, because we'll assume that we'll have a finite number of different communication behaviors, which will cover 99.9% of all realistic codes. Each element of the tuple is going to be a pair where one thing is the ID of the given process set and a CFG node where this process set is currently operating. The edges are going to be the possible transitions along the CFG. So individual process sets may transition, two process sets may transition to the same CFG node and merge into the same process set, and a bunch of other possibilities that may happen. All will have edges in the PCFG. So to give you an idea of what I'm talking about, let's go through an even simpler example and see what a constant propagation analysis would look like in the PCFG environment. This code, rank 0 sends to rank 1 receives from rank 0, and prints whichever value it got. And there's the CFG. This is a PCFG, not the entire PCFG. In fact, the PCFG is this gigantic, ungodly graph that you would never really want to generate completely. This is the part that we will ever care about, and as I'll discuss later, this is the only part we will ever generate. We're only going to generate a fraction of the PCFG, and for this example, here's the fraction. We begin with process set 0 through NP minus 1. So NP is the number of processes, so this is all processes are at the branch node B. Because the branch depends on the current ID of the process, well, we're going to split into three process sets, 0, 1, and 2 through NP minus 1. 0 is going to be at the assignment, A, 1 is going to be at the receive, R, and everybody else is going to be at node E, which is the end. So note, 2 through NP minus 1 is blocked. It's at the end of the application. There are no transitions it can make. They're stuck. Process set 1 is at the receive. There's no matching send, so again, it's stuck. It has no way to make a transition to the next node. Done. The only process set that can make progress is 0, so we allow it to make progress to its next node. And note that because of the assignment, we now know that x is equal to 15. Now, at this node, 0 is at the send, 1 is at the receive, and everybody else is at the end of the application. All right. Now we can match the send and the receive, because the send from 0 goes to 1, send from 1, receive from 1 goes to 0, so we can match them. We do, and now we know that 0 has advanced to the end of the application, x is still equal to 15, 1 has advanced to the print, y is now known to be 15, and everybody else is still stuck at the end. Now, 0 is at the end, 2 through NP minus 1 is at the end. Well, they're the same CFG node, so now we're actually allowed to merge these two process sets, which is what we do next. We advance to this PCFG node with only two process sets, 0 and 2 through NP minus 1 at the end and 1 at the print. Note that X has now become top. We've just unioned the state of X from one path where it was 15 and another path where it was unknown, so the union of these two things is top, which means we have no idea what it is. And the other side, the print is y equals 15, 1 is at the print, y equals 15. We advance that. We've now proven that process set 1 was in fact going to print 15. Now 1 is at the end. We advance further. Everybody's at the end because we've just merged the two process sets. This is the way these analyses are going to function. Do you guys have any questions now? But yeah,
how about asynchronous receives? Like I say I receive, or I send. How do you? Because with I receive you can't say that say process 1 or rank 1 would be in step R. It might actually be in P or something. You would have to wait your...
Yes, what you're going to be doing, I'll cover that later, because it's going to be a notable complication.
It becomes like a non-deterministic compared to a deterministic kind of...
No, it's not non-deterministic. That's an extra complication.
Okay.
No, what's going to be, you're going to have to be accumulating expressions. So you're going to have a bunch of expressions one by one. You're going to have some kind of FIFO buffer when one expression... If two expressions are identical, but just one is directly... Like if I receive from 0 and I receive from 0 again, then they have to be stacked up against each other, behind each other. It's going to be a much more complicated representation. The intuition for this is if you have a loop where you receive from a bunch of processes, you'll replace the expression that says I receive from 0, 1, 2, or whatever with I receive from 0 to something. It's going to be I receive from a set, and that's the kind of expression you're going to have. You're going to have to match that expression against these kind of more complicated expressions. But the major operation there is you're going to need to aggregate communication operations to deal with I receives, I sends, and so on. And then you can really postpone matching. You could, if you have non-blocking send and non-blocking receive, and you could wait till much later in the program to actually perform that matching. But I'll give you more information about that later. Leonard?
But I'm somewhat confused about why X becomes top at the end and Y becomes top at the end of the computation.
You're merging from two different, you're merging X equals 15 to X equals 2 unassigned.
But at that point, don't we know that the value of X is 15 since ranks 2 through n minus 1 will not be modifying X at all since they're already at the end of the computation?
Right, but X was only assigned on rank 0. Those other ranks never assigned it.
Okay.
So the only statement we can make about this larger set is that X equal to unknown. Right. Yeah, so one thing that I've kind of ignored so far is the fact that there's a difference between control flow graphs and data flow state. And I've not really differentiated two pieces until now. And in fact, there's a big difference here. In reality, what happens is we have two different entities. We have the control flow graph, where each node has a process set ID, and the CFG node where it's currently at. This is an ID. This is not an actual description of a process set. The mapping from process set IDs to actual descriptions belongs in the data flow state, as do all these facts like y equals to 15 and so on. The reason why this is important is that there should be a difference between the control flow graph, which depends completely on the application, and abstractions. Description of process set is an abstraction. We may want to have lower bound, upper bound, or lower bound, upper bound stride, or an actual list of unique IDs that correspond to this process set. Each different abstraction will be appropriate for a different analysis, and we do not want to bottle that up into the graph. The graph is completely independent of our analysis and only depends on the application itself. So that's why we keep these two things separate. So now I'm going to go into the actual data flow equations. And before I go into that, I'm going to, define what I need to define. For the control flow graph data flow, sequential case, we have a few standard things we have to do, we have to define, which is the state of the application, which abstraction we're going to be using to represent the application state, the transfer function that will represent how each statement modifies the state of the application, and finally a meet function, information union that combines the data flow state from different control flow paths into something that's true of all of them. With PCFG data flow, same basic idea. Like I said before, you have to have a map that identifies individual process sets and gives you the appropriate abstraction. You have to have the state of all process sets. Mind you, it's not individual process sets. You have a globule state where you may even have constraints that say that a variable on this process set is related to a variable on this process set in the following way. Finally, you need a few functions. You know, a transfer function, just like before, a meet function, and finally a special function to do your send-receive matching. One thing that's going to be important here, and one assumption that I'm making, is that no non-deterministic communication is allowed. So what I mean by that is if you do a receive operation, you have to identify your sender. You cannot say receive from anybody. This will be handled in future work, but right now that's an important assumption. And what I get from that is that the resulting communication model is interleaving oblivious. So all interleavings of the parallel processes have the same output. The benefit is that in any data flow analysis, I can choose which interleaving I'm going to be simulating and ignore all the other interleavings, knowing that they will all produce exactly the same results. And that significantly simplifies and optimizes the entire analysis. It will no longer be exponential. It's actually going to be much more reasonable as a result. Does the assumption make sense to you guys? All right. So going to the data flow equations. I mean, in the CFG data flow, things are pretty simple. I mean, you have statements, you have predecessor statements, successor statements. The way the data flow functions work is you take the data flow facts coming from your predecessors, you compute a meet over all your predecessors, and then call the transfer function to process the effect of the statement on the data flow state. And you produce either one resulting data flow state if it's a regular operation, or multiple if it's a branch, a switch, or whatever it is. With PCFG data flow, it gets more complicated. I mean, in the beginning, it's the same thing. We have to compute a meet over all our PCFG predecessors. Then we have to decide, do there exist two process sets in the current PCFG node such that they're sent and received and they actually match? So, well, yes or no. So first I'm going to go through the no match case, then I'm going to go through the actual matching case. If there exists no pair of process sets which have a send and receive match, it's simple. All we do is we let the data flow analysis choose, it's going to provide a function for that, choose which process sets it wants to operate on next, like which process sets it wants to advance along the, their CFG, next CFG edge. So then we're just going to call the transfer function of each such process set, let them advance, and take the resulting data flow state that, and advance it to the next PCFG node. The next PCFG node is identical to the previous one, except the selected process sets get to advance along the CFG. All the other PCFG successors, I mean, there's going to be a ton of these guys, all the other ones are ignored. Essentially, all we do is pass the special bottom state to all of them, and it'll propagate through the rest of, of the PCFG graph, and it'll just make no difference whatsoever. This is how the data flow analysis chooses which interleaving it's going to simulate, by saying, I'm going to look at the transitions by these guys next, and all the other possibilities are irrelevant. The reason why we even bother passing this along is to make the mathematics work out. In reality, we would never even generate that portion of the graph because it will have no effect whatsoever on the analysis. So that's the no match case. In the match case, well, we have to do something a lot more complicated. So suppose we have an operation send to process SE of rank. Rank is my ID, so you can have expressions that depend on your own ID. And another that's one process set. Another process set that's a receive operation is RE. They're a match if there's a subset S of sender, subset R of receivers, such that the composition of the two functions is the identity on S and R. Here's what I mean. Senders, receivers, this is what we want to see. I send to you, you receive from me. Similarly, this is good because you have these binary relationships between senders and receivers. This is bad because I send to you, you receive from somebody completely different. Similarly, this is not what we're looking for because the set S is too large. It really should have been smaller in order to have the proper matching. But that's a bit abstract, so let me give you how we actually use these matchings. So the example of before, 0 sends to 1, 1 receives from 0. Set of senders is 0, set of receivers is 1. The matching is obvious. What happens then is that we transition from this node to the node where 0 has transitioned and 1 has transitioned because they've both made the match. So this node. So what happens is that we pass the data flow state after matching from here to here. And all our other successors, again, we pass bottom, they don't even matter. And again, this is another way in which the data flow analysis chooses which interleaving is going to focus on. And it's not that, and most of these choices are not even going to be voluntary. These are going to be choices that depend on the analysis ability to match sends and receives. Is it good, bad, whatever. But the point is that it doesn't actually matter which matching it's going to do. Any matching that it can do is fine, and it's allowed to choose. Looking for a more complicated example, consider something like this, which is a broadcast from root operation. In the first iteration of this analysis, what we're going to have is we're going to have a send from X from process set 0 to process set 1. That's the first iteration, and receive from process set 0. So what we'll have is 0 is going to be sending to 1, but only 1. And the overall set of receivers is going to be much larger, 1 through np minus 1. What we have here is a partial match. And what we have to do as a result is split the set of receivers. I mean, what happens here is that 0 sends to 1, and only 1 from the set actually gets released. Everybody else is still stuck at the receive. So we'll transition right from this node to this node, where 0 is advanced, 1 is advanced, and 2 through np minus 1 is still stuck at this receive. And this is how it turns out. This is how we pick that we're going from this node to this node. Note that because of the split, this node has more process sets, more by 1. And we'll do that. We'll see how this works in an example coming up right up. But here's the overall, the way the Dataflow equations work. We first merge the incoming states. We decide whether we have a match or no match. And in either case, we pick some successor PCFG node to propagate our Dataflow state to, and then everybody else gets this bottom symbol. So, you guys have questions before I get into a bigger example? All right. So now we've gone through the basic structure of these formulas. Let's actually have a real example to see, with fixed point of, with getting a fixed point of this thing and so on. This is the same example from before, where we have exchange with root operation, and well, this is the code. Here's the CFG. Here's the PCFG. Note that PCFG looks very much like the CFG for all intents and purposes. I mean, we have, we see the loop here, we see the back edge, essentially the same level of complexity. So to begin with, we start off at the top of the application, process at 0 through np minus 1, all processes, starts at node A. We then transition to this state, B and G, where process at 0 is sitting at this assignment B, and everybody else is sitting at this receive. Now, 1 through np minus 1 is now stuck. It's sitting at the receive. So the only process that can make progress is 0. So it makes progress, and it knows that now that I is equal to 1. And note one difference. We recorded this fact in all of our states. So we now know that 1 is equal to I. So the lower bound of the set is now, is an equivalence class of all the things that are equal to 1. Then we advance one step further. Okay, the first send. We know that I is equal to 1. This is the first iteration. So we know that 0 is sending to I, 1 to 1. 1 is receiving from 0. We match these up perfectly. But because we only have one such send, we have to split the set of receivers. So the process set 1 has received. It gets to move on. Everybody else, 2 through np minus 1, is still stuck at that same receive. Now we have a send on process set 1. It sends to 0, so it definitely cannot match this set. It has to match that receive, so it has to match this receive. It does. We advance. 0 is now at this increment. 1 now gets to advance to the end of the application. So it's done. 0 gets to process the increment. Note how I changes in both these cases, because this is a global state for the entire CFG node. And now we're back at the top of the loop. Note that in the PCFG world, we have just gotten to the top of the loop. Because note, the loop is the loop that has all these different process sets. Because the real behavior of this application is we have 3 real process sets. Set of senders, 0. Set of processes that have already received, and set of processes that have not yet received. So we really have 3 process sets. And that's where we're going to be doing this fixed point iteration. Now, we advance again. We perform the send receive matching. 0 matches 2. 2 gets to advance. We match it back again, just like before. Now, process set 1 and 2 are at the end of the application. We merge them. So now 1 through 2 is the end of the application. And we increment I. Great. Now we're back at the top of the loop. And now this is where the important stuff happens. Because we've been here before, and we've had state at this node before. So now we have to merge our previous state of this node with our new state of this node. So originally, this set was actually 1 to 1, or I minus 1 to I minus 1. We have to merge the old set with a new set. Well, look at the lower bound. It was 1, I minus 1, I minus 2. We pick the union of these two values, so it's actually 1. the upper bound, 1, 2, I minus 1, I minus 1. Pick the union, I minus 1. So the real set here is 1 through I minus 1. Same thing up there. Before it was 2 through np minus 1, now 3 through np minus 1. But the common point is the I. So the real set here, the fixed point solution, really is I through np minus 1. And this is the loop invariant, that all processes up to I have already performed the communication, and I through np minus 1, you still have the communication remaining. And if we went through the loop again, we would know that this is in fact the fixed point and so on. I'm not going to go through those details. I'm going to go through the interesting bit. The interesting bit is what happens when process at 0 leaves the loop. So when it leaves the loop, when it leaves the loop, it's now sitting at the end of the application. That's fine. But and because 0 and 1 through I minus 1 are the same node, we get to merge them. That's great. The other thing is I is now greater than or equal to n. Well, note what it tells us about this set here. The set I through np minus 1 is empty when I is greater than or equal to n. So by the time 0 leaves the loop, leaves the send loop, we've proven that the set of receivers that have not yet received is now empty. So we get to delete that process set and move on with our lives. At the end of the application, we know that the process set 0 through I minus 1 with I greater than or equal to np. So all processes are at the end of the application. We're done. In the process, we've shown that this send matches that receive, this send matches this receive, and they do have this pattern where 0 exchanges with everybody else. So enough with the analysis details. What have I done so far? So right now I have an implementation of the basics of this framework. Essentially all the stuff I've shown you so far has been implemented. It's done in terms of the ROSE compiler framework, which is the source-to-source compiler being implemented at ROSE. It can deal with C++ Fortran 2003, so it's convenient for my purposes. So I can deal with these patterns. Specifically, the abstraction I can deal with right now in the implementation is matching I to I plus 1 to I plus 1, these kinds of matchings. What I've designed is not currently implemented is expressions like this, which have plus minus times divide and mod. And, so essentially it's, the nearest neighbor communications transposes, that kind of stuff. So there are abstractions that can capture this. Yeah, they're not currently implemented. What's coming up next is non-blocking operations, and that's where it gets a bit interesting. So I was answering Sanjan's question, where in this application, it's an all-to-all pattern. So everybody I sends, non-blocking sends to everybody else, and then can go one by one receiving from everybody else. Great. What's going to be is that this send, so the receive is just like before. We're going to be receiving from some process I in each iteration. But the send, we're going to have to accumulate a pattern that corresponds to this entire loop. It's going to be a send to a set of processes. And the result is more complicated matching rules because this is an unbounded number of individual send operations. We have to match unbounded number of sends to unbounded number of receives or bounded number of sends. There are going to be a bunch of these complicated combinations. It just makes the send-receive matching rules more complicated, but that's already been designed, not yet implemented. The fancy stuff comes in the future. Right now the framework is intra-procedural and needs to become intra-procedural. I have ideas for that, but still premature. Dealing with non-deterministic operations like receiving from MPI any source or lock and unlock. So in the lock and unlock, when I lock, I have no idea which unlock operation I'm receiving from. That's in the future. The intuition of how I'm going to be doing that is I'm going to be expanding the PCFG graph to a much larger graph, which is going to have essentially the same properties, but for non-determinism as opposed to for communication. Same kind of interleaving obliviousness, but for non-determinism. And obviously, there's a ton of applications to look at. In particular, one thing I'm looking at right now is turning SFOT, which is a Monte Carlo transport code, into what's it called? Dataflow kind of application, because when you look at the source code, it's this very highly it is a very highly structured thing. You have a bunch of tasks, and each task goes to a particular process, and it's statically scheduled, obviously. And then every process, after doing every task, it performs a gather to tell root, what they've discovered, and you do this in phases. But there's no reason to do that. If you knew that this was the structure of the application, you could actually make this essentially a data flow application, which you can farm out as a MapReduce task, really. But that's not how it was written, and unless you know this, you could never do it. And these are some very preliminary results. In fact, the graphs are not quite aligned because I just pulled them together from some large-scale runs. This is the number of nodes I'm running this application on, and I'm just doing two simple optimizations. The first optimization replaces all their gather operations, which were done using point-to-points, and replaces them with MPI gather. which has mixed results. Sometimes it's better, especially, well, it really varies on the system. And the other one is it takes all those individual gather operations and shoves them all at the end into one big gather operation. And that's the purple line, and it tends to have better results. In fact, more consistently and importantly, at large scales, it improves performance. Even for an application where most of the time is in fact spent in computation, not in communication, but by doing communication sanely, as opposed to this very strange, I think, pattern, you can do a whole lot better. So this is just what I'm doing, just to verify that once the analysis is completed, it will in fact do useful stuff, and that's what it's looking like. Last thing for me to be doing here is actually turning this whole thing into a map-reduced kind of application, which really is what it should be. It really is a master worker kind of application, but it was never coded up this way. So to summarize, the point of this talk is that Dataflow is nice. We like Dataflow. It's been around since the 60s. It's very useful. It's just not very good at dealing with explicitly parallel applications. And the whole point of my work is taking all those old techniques that we've gotten over the last 40 years and bringing them to the applications we're writing today. And think of it as just a bridge. And currently, my current work is on message processing applications, but the overall framework should be working for logs, workflows, and so on. So at this point, I'll just stop and see what you guys have to say about, what do you think are uses of this kind of framework, where it should go, that kind of stuff.
So I have a question about sort of the scalability or any kind of analysis like this that depends on sets.
Okay.
In the small examples it looks quite reasonable, but we all know in sort of real programs things are a lot more complicated.
Right.
And so the sets are likely to be much larger.
So to give you an example of a complicated example. So, in fact, perfect. All right, so non-deterministic example. You do, again, simple structure, but an opportunity for sets to blow up significantly. So you do, let me see, this is rank 0 for I equals 1 to NP minus 1, receive any. So you're receiving from any process. You don't care which one it's going to be. It's a gather or reduce operation. It's a basic structure for all these things. And rank non-zero is sent to 0. The problem here is that what's the set here? After each iteration, you have no idea what the possible receiver is. So you can have an unbounded number of possible process sets for who possibly sent to you. But it doesn't have to be this way. When you go through this loop, before what we had was process set 1 through NP minus 1 was left, then we had 2 through NP minus 1, and so on. But you can't do that because you don't know when you receive which element of the set you actually pulled out. But for this application, you don't care. All you really need is the following abstraction. It's really 1 through NP minus 1 minus set u, and the size of u is equal to I. That's the abstraction you want. And that's going to get rid of all the explosion of possible sets because you don't really care for this example.
How do you automatically choose the right abstraction?
I don't know. I think the appropriate analogy for this entire work is think of the first papers in pointer analysis, ALS analysis. It's too early to tell. I do not have the experience to know how to choose these things. And I think it's going to be another 5 years before we have enough experience in actually using this thing to do anything useful before we know how to choose abstraction for common communication patterns. Another good example is I have an abstraction for representing Cartesian communication expressions. Well, what if the appropriate thing is something that's more multiplicative? It's like what the user is really doing is a reduction tree, and you have to know that after log number of iterations, you've covered all processes. I don't know how to choose the appropriate abstraction for those expressions. It may be kind of greedy thing where you back off after you figure out it's a bad idea. Maybe something more theorem proving, like where we have something even more powerful. I'm really not sure just yet. Or maybe we just try several, keep them going for a while until we choose which one we really want. But yeah, right now I wouldn't even know. Right. No? Then thank you guys.